Okay, I will do a small recap just to fix where we are. So remember, we were looking. So actually, last time I think Justin made me say something wrong, or at least not very precise. I was looking on the torus, and we derived the first order condition on the torus because I was thinking I do the simple case, and actually I'm not sure anymore now that I think it again. So let's start from beginning. So the problem is I want to do phi for 2 on the full space. And what we did is that we considered the GFF on R, on R2. So the GFF is everywhere. It's not like in the picture yesterday in the talk by Felipe. Where is Felipe? Yeah. Okay. It's everywhere. This is simplify things. You could consider periodic domain take limits, but then everything is moving. So this is the simplest situation if you want to understand infinite volume limit. Is not the only one. And then we were putting a tilt, usual tilt, which depend on a bounded set, okay? Bounded domain. Think a box, okay, of size L, for example, okay? So this is, could be, and then I want to send L to infinity, okay? And so this will be the measure mu phi, so this is on a finite volume, and V lambda phi is just the interaction, but usual interaction, now we know everything about this. We normalize in the right way. I already imagined that I took the UV cutoff to infinity. Okay, we know this random variable exists, it's a random field. It grows logarithmically. We know everything about this, so I can integrate on a bounded domain. This is almost surely finite. And then somehow the proof that we did for Nelson, it will work also in this new context, okay? Because essentially there is no much difference from what we did. So now the problem is, so the problem we want to solve is to show the tightness of this family as lambda goes to R2. Tightness on, let's say, to be vague. Okay, this is a family of measure at least which takes value usually in this space, and you want tightness in this space. Of course, to do tightness, you have to find compact subsets. So actually, we will consider really more precise norms, and you prove some norm bound, okay, uniform norm bound. Okay, essentially, if you're not familiar, I think in this business, this is like analysis. So in the business of analysis, is all about having control of quantities, okay? And then when you have this, then you can cook up any nice, elegant argument, but at the end of the day, you have to do the hard work to find a bound, okay? Sometimes it's elegant, sometimes it's not elegant, but that's the goal. So here would be something like this. So what we aim for to find some norm. Okay, we know that the base measure is the Gaussian free field, and infinite volume, this is absolutely continuous. So the norm, it cannot be better than the regularity of the Gaussian free field. Actually, I don't remember the norm. I think any norm would work. For example, you could take H minus 1 for some reason, let's say, some negative Sobolev norm, okay? Gaussian free field is regularity epsilon minus epsilon, so this is largely sufficient. And then probably, again, this is in the full space, so you have to put some weight, okay? So some weight, okay? Okay, so some norm like this, and then to some power, and then you integrate with respect to the finite volume measure, and then you want to take the supremum over the volume, and you want to show that this is finite. Okay, so this is somehow what you have to have in mind. When I talk about tightness, you have to end up sooner or later with a bound like this, okay? And then a set like this is compact in S prime, okay? Yeah, I took the integral with respect to the measure. So this is just the moments, some moments of norms, but the point is that the measure depends on the volume and you want uniform bound. And you need a weight because this is, again, okay, this is a field in the full space. So imagine, some weight, okay? So essentially you want to discount region very far and you want to discount very small oscillation, okay? And then if you have a bound like this, you can prove that the family of measure is tight. And in this case, for 542, I cannot prove there is a limit. This is like open problem for you, for a younger generation. So in this approach, I will show you there will be a problem. A problem is essentially that somehow we are in a situation of somehow negative curvature, or at least the curvature is not clear that it's positive. So I will show you later today. My plan is today finish in 2 dimension. I will go a bit fast. I hope that speed is okay. Okay. But please complain if speed is not okay. Is it okay so far, or I'm too fast? Is it you are getting bored? Okay. If you're getting bored, you know where. There is the sun. It's a nice day today. Yeah, so I will try to look with some speed to the other case, because tomorrow and after tomorrow I want to look at 3 dimensions, so we get more fun. Okay, but somehow I want to show you in a situation where you can prove that the limit exists. So here I cannot, I have tightness. Actually, there is a reason why they could not be. So in general, if you put lambda here now, if you put some constant, imagine that here you can always put a constant. I just don't write it down because I cannot do anything with that. So imagine that there is, and all our estimates are like somehow uniform in this constant. This has not to be small or large. But somehow what should happen is that these measures are not unique in, I think, with large lambda. I don't know. You can expect uniqueness only for small lambda. Okay. Recall that there is another scale because I take the GFF with the covariance like this. So I have a scale given by this one, which is the scale where the GFF correlation decay. So somehow this lambda large and small is to be compared with that scale, okay? So essentially we cannot, so just I made a remark. So we expect unique limit only for small lambda, okay? And for large lambda, I think, but I don't remember exactly in this case, but certainly for small lambda, unique limit, and for large lambda, 2 limits, okay? Possibly 2 limits. 2 limits. So not 200, 2, okay? Because essentially there will be, you could have a phase transition, like thinking about Ising model. So think model Ising. So Ising model has a low temperature phase where you have actually 2 infinite volume possible limit, one where the field is tangentially positive and the other where it's tangentially negative. Here we create some non-convexity, so you have to think that your potential looks more a non-convex thing, and it could be that so you have 2 configuration, a positive and a negative magnetization configuration. Yes, Carl?
Because your GFF is periodic.
No, I told you already that it's on R2, so it's not periodic.
No, on lambda. How is it when you take the finite box?
No, again, okay, I take the measure in the full space, I take only the interaction in the finite box. Okay, so you think this field looks like this. Everywhere is Gaussian free field, so this is GFF, of course. But then in the bounded domain, looks like 542, okay? So I just perturb the measure in a bounded domain. Okay, outside is unperturbed. Of course, Gaussian free field has decay of correlation, so you have to think that somehow you will influence a bit what happens outside. You have this decay, and actually, yeah, okay. But then we take so we look, essentially what we are doing is that a norm like this will look locally because there is a weight, and then essentially you want to prove, in theory, to prove that the limit is unique, you want to prove that what happens very far don't matter anymore, but we don't. I will show you that because the potential is non-convex, it's not obvious what to do, okay? So this is the situation. So just to remember that we found the Euler-Lagrange equation, so first order condition, which looked like that. Essentially was the expectation of the derivative of the finite volume measure in W plus Z. Remember, I had W, which is this dynamic Gaussian free field that I introduced, and then I had Z. Ask question if you feel that you don't remember, and then there is a trial configuration because I'm trying to write this first order condition. It's some kind of weak formulation, okay? For any process K which is adapted and in H1, you need this plus the form between Z and K to be 0. Okay, this has to be true for any K in a set which is like H1 of time and H1 of space and adapted. Okay, so but let me put adapt. Yeah. Okay, K is remember depends on time, space, and omega. Okay, so omega in time you have to be previsible. Okay, and this quadratic form was just the integral of essentially this H1 norm, which if I write somehow you can write in many ways, but let me write it in this way. So we see the covariance of the Gaussian free field, and then there is something like this. Okay, this is the time derivative. Okay, so this was our problem, and this is the first order condition. And now the point is that I want to treat this, you have to think that this is like an elliptic equation for Z. Okay, so this is the intuition you have in mind. Okay, the model does not look like, but you see there is a Laplace. Of course, we could derive a better equation. Okay, remember from this we derived an equation which looks like this, because for every K you derive a condition, and the equation we got was like this, but I don't know really how to use this, so we will use only that. So we derived an equation which looks like this. Okay, this was like the gradient of the lambda. I leave it implicit because it's not in the direction, yeah, at some point. Okay, so it was something like this, minus. So there is minus the gradient. Okay, it was something like this. And there is renormalization inside. You have the weak product, so everything is there. I don't know really how to use this. This is for an open problem for me. It's an SPDE, so it's a forward-backward SPD if you want. Okay, forward. We call it forward-backward SD. Forward-backward. Yeah, we call it forward-backward SD, but it actually is a SPD, but whatever. Okay, you give fancy. It's not a very precise name. Okay, so you see it's a difficult problem. In time variable is just an ODE. Okay, and the time variable is an ODE because you specify the derivative. But the problem is that the drift at time S depend on the law, conditional law in the future. So you have to, okay, so just to have an intuition. Okay, so the process start essentially, this is Z, this is S. The process Z starts in 0, so all these trials are 0 at the origin. Okay, then it starts in 0, then it go forward, and then you are at time to know what to do at time S. You have to sample the law in the future up to time 1. You have to compute this. This is like this score-based system. I told you we are doing machine learning here. And then you have to take the conditional log. So if you want to simulate this, at this time you have to run a lot of simulation in the future. and then you try to find a consistent law which fit into this framework. Okay, so this is not very easy to solve. We are not actually, we don't have to solve it. We know the solution exists. It's the minimizer. I have to guarantee the minimizer exists. And are the 200 pages of the lecture notes, because you have to relax the problem, and then this creates a bit of technical problem. But let's imagine we have a minimizer, and then somehow the minimizer satisfies this equation. So the equation is solved via the direct method of the calculus of variation, like you solve any elliptic problem. If your elliptic problem is a first order condition of a variation, convex variation of function, or even on convex, you take sequence of almost minimizer, you try to do it in a space where you have some compactity, and then you get a limit, and you get solution. Okay, solution theory, it's easy in this case, because we use this gradient flow structure, if you want. Okay, it's not really a gradient flow, but the process of minimizing gives you the same result at the end. The point is that now I want to use, so the equation I know how to solve. If it was not a gradient flow, if you put a general function here, I don't know what to do anymore. Okay, this is the point of having the gradient of a function. So I don't have a general theory. Yeah, you could do a theory if this function is Lipschitz with a small Lipschitz constant, because then you can just do a fixed point in a space of law. Okay, because you start, you do it. Okay, so think about this in this way. Well, this is, in our case, is not Lipschitz function, okay? Because, no, this case, I don't know how to do anything with this equation, okay? But if you replace gradient V, well, if you have, for any gradient of something which is bounded from below, you can run the direct method of the calculus of variation. For a function which is not a gradient of something else, but is Lipschitz and with a small Lipschitz constant, then this is exercise for you. You just do Picard iteration. Okay, you start with a trial, you continue, and the Lipschitz condition is very easy. Okay, this is no-brainer. Okay, the problem is that it's not like the theory where you can start at the beginning, you can continue. This is a global problem, so you cannot do for small time and then glue the time. Okay, so this is a forward-backward equation. So we call it FBS. Okay, so let's use it, because I'm talking, but I'm not showing you anything interesting. So our point is that I want to use it to get the tightness of the measure. So we have to recall, I didn't prove it. The proof is in the notes, it's easy. It's not obvious, but somehow you want to understand what is the relation between the minimizer. So this is now, it's a minimizer. Okay, so this equation is satisfied for the minimizer. So if Z a minimizer, there could be more than one. I don't have any uniqueness, the potential is not convex, but for any minimizer, this property is true, is that the law of W1 plus Z1 is exactly my measure, okay? So this is all the point to do all these fusses, because we have this. And therefore, if I need to compute quantities like this, I just need to give estimate of the solution of this variational problem uniformly. So we are looking for estimates on Z uniform on lambda, okay? I removed the tightness, but let's okay, essentially our goal is now to estimate something like this, like W1 plus Z1, let's say some space like this, and some power P uniformly on lambda. Of course, the minimizer depends on lambda. The Gaussian free fit does not, okay? So essentially this will become our goal, okay? Now I forget the original measure because it will be a byproduct. Do you have a, Hugo, you have a question? You were, yeah, you had a question, yeah, you said.
I do not understand how you can compute the integral that you just erased.
Yeah. What do you mean? So this was, sorry, I erased, but this was a measure on trajectory. What do you mean how you compute? I don't compute it, I'm telling you. Maybe I don't understand your question. So this is, so this is this measure, so it's just a perturbation of the Gaussian free field. And then I have a norm here, put whatever norm you like, and then some power. So what you mean compute?
So you link this one to this one?
Yeah, so this is the point, okay? The point is that I solved this equation, if you want, and I know that it's not that every solution of this equation has this property, but if Z is a minimizer of the variational problem, which I didn't wrote, sorry, but you remember the variational problem we had at the beginning, then it has two properties. One, it solves the first order condition, and the other property it has, this I didn't show you, so please, yeah, maybe your doubt is about this because I was a bit fast, but this is very important. Any minimizer has the property that the law of the minimizer is exactly at time 1, is exactly the 542 measure. Okay, so I found a process on this enlarged probability space. I found a process which has a marginal, which is the measure I want to sample from, okay? This is like this diffusion mode, okay? These are my cuts, and this is my diffusion, which converges to the cuts at time 1. So at time 1, I have 542. All the rest is something that I added to be able to use analysis, okay? Otherwise, 542 is a probabilistic object, so I don't have, it's a measure defined as a perturbation of another measure, and I show you the Nelson proof. This is a kind of a probabilistic argument you can do. But I want to do stochastic analysis, so I need an equation. Yeah, it means I wanted just to say that zeta 1 depends on lambda. Yeah, if you want, I can write it also here. Yeah. Yeah. So this is a minimizer of the potential V lambda, okay, with V lambda. So can you precise your question now? So no, yeah, but you see, if he has a problem, it means that half of you has also the problem because it's average guy in this very good group of people. So do we understand this point? Yeah, ask. Yeah, sorry, that's why minimizer of F lambda. So let's rewrite what is F lambda, just to be clear. You see, this is the main point of this lecture. So if we don't understand, you see, I slowly going to do things which are usual to things which are under the title are new things, okay? You never saw them, so it's normal. I don't think you have seen them before because maybe various ingredients are there, but how they use together, it's new. By the way, this was work with one of my PhD students, Nikolai Barashkov, okay, which is now his MPI in Leipzig. So F lambda was this functional, essentially depends on this trial, and I needed to take the expectation and then V lambda plus Z, and this depends only on time 1, and then I have the representative for the entropy. Okay, so so Z is argmin. So let's say Z lambda is argmin of F lambda. Okay, so I look at the minimizer. This minimizer has this property. So this implies. So this is, I didn't show you. That's why you are perplexed, because you don't see. I think I was a bit fast here, but that's the point. So is it true? You can prove that the law under this probability measure of W plus the minimizer, let's call it, is exactly, at time 1, is exactly my target measure. Okay, this is not obvious because what I told you at the beginning is that the Gibbs measure is the solution of a variational problem. Then I wrote the variational problem, and then I somehow re-elaborated and I created a new variational problem which is related to that one. In particular, the free energy is the same, but it's not obvious that this tells something probabilistically about it. But this is true, okay? Its proof requires half page, but it can be done. It's in the notes, you find the proof at, I think it's around lemma 25, lemma 26, I guess. Okay, so page 24. Do we want to do it? No, let me not do it, okay, maybe, because otherwise I don't. So somehow this is a computation you have to do, it's a fact, and it's not is intuitively obvious because the minimizer should have a particular meaning, and and this was the minimizer of the original problem, so they should be related, but it's not. Yeah.
Did it tell you that if there is a minimizer, then it's unique?
No, there could be more because I don't know any. Yeah. No, because the potential is not convex. Okay. But it's not obvious to me. Maybe, probably in finite volume, you can prove there is a unique minimizer, but I don't know exactly how to do that. Okay, I would expect that if you are in finite, like now, I mean, in this case, in this particular case, phi4 with a finite volume interaction, there should be a unique minimizer, but I don't know how to prove it easily. I will show you a case with the exponential interaction, I can prove it, okay? And I mean, here, if you try path coupling, well, this is a solution of a problem. So for any minimizer, they have to solve this problem. You try to compute the difference of two minimizers, and you get stuck because the potential has a part which is very non-convex. Okay, this is related to the fact that, yeah, I mean, in L infinity, in L infinity, the curvature is infinite in this case. Okay, it does not happen like yesterday with Justin, where things always go together. Here, things can diverge, and you have to prove that in average they go together, and maybe you prove that. So this is an open problem. It would be very interesting for me if you find a solution to this problem, because it should be true at least in finite volume, or for small lambda in infinite volume, that there is a unique minimizer. But we don't know, it's an open problem. Recently, for the parabolic equation, which I didn't explain, so Langevin dynamics, the infinite volume, uniqueness of the dynamics in infinite volume has been proven via logarithmic Sobolev inequalities and things like that, okay? So by Bauer-Schmidt, Dugalier, and Weber, okay? There is a paper on arXiv. This is very nice, mixing functional inequalities, and it's not obvious, okay? Infinite volume should be easier, but I know very little about these equations, okay? This equation has not been studied, and not in this way. They are somehow optimization condition for stochastic control problems, but usually people look at finite dimensional stochastic control problem or without this kind of singularity, so it's a very different problem, okay? For example, the direct method, dynamic programming, the solution should be Markovian, okay? This object should be some function, let's call B of ZS, okay? Because the solution of the control problem with finite terminal cost, it's Markovian, okay? So I think this is, but we don't know anything about this B. Usually it's given by this dynamic programming principle. You have to solve Hamilton-Jacobi equation for that, but will be a Hamilton-Jacobi equation in infinite dimension with polynomial like initial conditions or singular initial conditions, so it's very complicated. So the idea is that you don't want to look at these things which in finite dimension are the classical tool, because they become useless in infinite dimension, and I'm just looking at the problem in this way. But again, okay, this should have a unique solution in finite volume, but I don't know how to prove it, okay? This is future work. I'm now explaining you a well-understood theory. I'm explaining you an hopefully interesting theory which has a lot of open problems, okay? So you cannot complain you don't know what to study. There are a lot of problems in it. Do we have other questions? This is an important point, okay? So again, I don't prove it for you. See page. Okay, maybe look at it, or we can discuss. It's a computation, and I don't have any intuition about this computation. So I'm a bit, see page, page in the notes, 23, okay? And again, it's not that once you saw the proof, you don't gain any more knowledge than what I wrote. So usually I like proofs, but in this proof, there is no wisdom. It's just, you have to, this is what is the intuition, and you verify that the intuition is correct. And the proof is a bit, not artificial, but does not contain any, there are some interests. Maybe I will mention some detail about this later. But I just want this fact, okay? The minimizer has this very important meaning for us because they represent the phi4 measure. Therefore, if I need bound on the law of this random variable, which is new, so this will give me tightness for the measure, okay? So this gives you the tightness condition, become this bound on the on the minimizer uniformly in the volume, okay? The difficulty is not the bound, the difficulty is the uniformity in the volume, okay? Okay, let's try to do some please go back to this question if it's not clear. I will try to build a bit of the proof and then we discuss later if it's fine for you. But somehow, yeah, this gives you that condition in the sense that if I can prove this, I have a, well, if I will prove somehow that the sequence of process is tight, and in particular, the end value is also tight, okay? So you will have limits processing. So you have to think of this object, so you have to think how you think about this object. So W plus Z, this is what is called, what we call the interacting field, interacting. Well, we can call it also X, okay? So this is the Gaussian free field. This is a perturbation, like a drift term. And this is the phi4 to infinite volume. Okay, so you have represented, so this field at time 1 is the phi4 field. Okay, so I call it improperly the phi4 field in the finite volume, just because at time 1 is exactly what I was starting with. And then I represented it as a sum of Gaussian free field plus something else, okay? Something else is also quite nice, okay? Remember that Z is in H1 of the space and H1 of the time, but in particular it's very smooth with respect to the Gaussian free field. Okay, so I wrote an interacting theory. I wrote the field under this measure as the Gaussian free field plus a perturbation. This is like in Girsanov theorem. Now you write a diffusion as Brownian motion plus a drift. Okay, so that's why I'm saying we are doing stochastic analysis, because we are looking at the pathwise properties of this measure. Okay, I'm not interested in the measure as measure of events, but I'm looking at the path of the measure and I'm trying to exploit the property of the path. Okay, so this is stochastic analysis. In the sense that you do for SD. We are not using SD, but Ito was not planning to do SD. He was planning to have a theory, pathways theory of Markov process, and then SD was what he found. Okay, we found this and I decided in this course to concentrate on this thing. Okay, so we have a coupling between the Gaussian. So we have in particular, this representation give a coupling. So if I write like this, actually it's even precise, coupling between GFF and phi4. Okay, I don't know if it's an optimal coupling, but I don't care optimality, I care that it's a useful coupling, so useful. Okay, this is a coupling in the sense of just 10 nodes, okay? You have a pair, X1 and W1. W1 is distributed like the Gaussian free field on the same probability space, and this is distributed like the phi4 measure in finite volume. And actually, this coupling is very nice because the difference is Z, and Z is in H1. Okay? Let's say, well, with a weight. Okay, I don't care. So this is finite. So the coupling is very nice, okay? You have two random variables which live in a space of distribution, but their difference is smooth, okay? So, and then you could define a improved Wasserstein distance, and this coupling would be the fact that these two measure at a finite distance, because there is at least one coupling, okay, between them. We don't use this, okay? But think about this as a relation with coupling. So this is telling you that this measure, nu phi, you see, you have a different point of view on this measure. Now you have the Gaussian free field, so this is GFF, And in the essentially, what will happen is that Z is different from 0 only very near to this volume. So essentially it looks like this. And then you have, you have this measure, but it has the same fluctuation, but just shifted by Z, okay? So this will be the 542 measure. Yeah. But the shift is smooth, okay? So you have very nice pathwise point of view on this object. So I have this in mind. So think about the picture of Felipe again, so you can be very precise. You can do this picture, and somehow the 5-4 will look similar. Okay, so let's try to use this now for, I want to prove tightness. You need to estimate, so I want to estimate the solution that I just erased, sorry. But somehow I want to prove something like this, the uniformity in the volume, so I want estimates of the solution. So how you estimate PDs? You do, for example, energy method. You test with a function, and then you try to get relation with some quantity, okay? So essentially we test the Euler-Lagrange equation, and we take K equal some weight times Z, okay? This is a weight. And this is the minimizer. Okay, so this is my test function. You will be admissible for. Yeah?
So when you write x equals the weight of z, outside of the domain lambda, should we think that z is 0?
Well, Z solves an elliptic equation, so it cannot just be 0 outside. So there is a source term we were discussing also last time. I will rewrite things, but somehow Z is governed by an elliptic equation where the source term is only in the domain. So inside, this is acting to push it away from the Gaussian free field. But then outside, you have this decay. So outside, the decay of Z is essentially exponential of size 1, because you have the Laplacian with the 1. And this is, yeah, you could write a mild formulation where you write Z as the green function of this integrated with the source term, and this will allow you a precise estimate. Yeah. So very far is essentially 0. Okay, it's decay exponentially outside the domain. But it cannot go abruptly to 0, otherwise this part will be very large, okay, because this is an H1 norm, so you don't want that. Okay, so when we test, so I erased exactly this line, but I could rewrite again. So this was 0, and then you had the gradient of V of lambda, W1 plus Z1, and then I test with exactly Z rho, and then I have the energy of Z rho with Z. Okay, so this depends only on space, okay, depends only on X. So this is just a function of X, so it does not depend on this time variable, fictitious time variable. Okay, you just test, and now you have to do a few computations, so let me skip those computations. So what does it look like? Up to error terms. So you see, this is a strange equation. You're integrating essentially in space because you are taking this functional derivative. So so let me write, but you integrate also with respect to lambda. So how does it look? This, remember, this was a fourth order polynomial. You take the gradient, so this third order polynomial is essentially the weak product of W1 plus Z1 cube, if you want. And then you multiply times rho Z1. And then this form up to error term, which I will ignore, because you have to commute the weight with the Laplacian, essentially. This object will become essentially up to error term, let's write it in this way, the integral of 1 minus Laplacian 1/2 of rho 1/2 Z L2, okay, of X ds. This is Z dot. Okay, so what I did, so imagine this is like rho Z and then 1 minus Laplacian Z dot, sorry. Okay, and then I want square root, I separate the Laplacian in two parts, this gradient in two parts, and I want to take the other part here and to create this quantity, and you have to pay some commutator, okay? You want to symmetrize this quantity here. So this up to error terms, which are small. Okay, I can control them. That's not a problem. Okay, now inside this expression, so this is good. I want this. This is a quadratic form. It's not clear that what I'm saying is that it's positive up to error term, and the error term are controlled actually by this. So essentially, this quadratic form is this. Here you have a good term because you have the term with Z1 cube. So this produces another good term, which is rho Z1 to the power 4, like the other day. So we have two good terms. So these are good guys. So these are the good guys. And then all the rest are the bad guys. Okay, who are the bad guys? The bad guys, let's list them. So you have few of them. You have like W cube, the usual ones, like infinite volume. But now you have the weight also to integrate. And then you have W2, Z squared with the weight. And then you have W with Z cube with the weight. Okay, so these are the three bad guys of the situation. So this is not going well. Okay, we have two good guys and three bad guys. So that's going. Let's hope that is going to work. So we can run a how you call it, bet on who will win. Okay, you know because you read already the story. But somehow, now I skip the computation because these now are the same. So what we are doing, so you have 0 equal all this guy, okay? 0 equal good guys plus bad guys, okay? Now, what you want to show, essentially you want to show that you can control the bad guys with the good guys and other terms. So what is the point? So here you have to look at this object as an equation for Z. So Z is the object which is very complicated because it summarizes all my interaction. And W is the object which I like because it's Brownian motion and everything. So you have to consider this an equation with you put inside W and you get out Z. And now you want to estimate Z in terms of W. Okay, that's the goal. The good guys help me because somehow these are quantities of Z which beat the other quantities of Z I don't know about. Okay, so this is the only information I have about Z is essentially these two quantities. So when I try to bind these quantities, I have to use those. Okay, and this is the same game we played. So let's try essentially the size of the bad guys. This is the same game. You just have to trust me. The only thing, we did it in finite volume without the weight. So doing with the weight, just you need to understand how to deal with the weight in functional inequalities. But essentially, it's nice. You have to put some weight with every of the function in the right way. Okay? This is a non-trivial game because you see that here you have Z. Here, if you want to control, this is essentially the good guys. So the bad guys is controlled by a quantity which depends only on the noise. Let's call it Qt. Depends only on W. So actually on W, W2, W3 is the kind of norm I wrote before. It's some norm of W. And then there is a small quantity. So here there could be a large quantity. This is small. And then you have the good guys, okay? But the good guys who are in reality, so they look like, so what is this? Is the L4 norm weighted with power 1/4 in our condition. So it's like this, 1/4 Z, 1 in L4 to the power 4. This is one good guy. And the other norm is essentially 1/2 Z, 1, H1. Okay, essentially this is what is this norm up to equivalence. Okay, And now you see that the game is more fun than when you do finite volume is fun, and then this is more fun because if you want to use regularity, you have only write a certain weight, and if you want to use integrability, you have to write another weight. Okay, so when you start to do functional inequalities and you get L4 norm, would be better that Z is always accompanied with this power or higher power, okay, because the weight is decaying, so you can handle higher power. And okay, now one has to do the kind of things I did. I don't do it again, okay, but this is now, you can prove something like this for the bad guys, okay? This is the goal, and you try, and this is working, okay? So how does it look like this Q? So Q looks like essentially is a sum for n, which is 1, 2, 3, of some norm of W, n, with some power of the weight, which maybe could depend on n, because you have to use different inequalities, with some power which depend on n, and here with the C minus kappa. Okay, so they look like that, okay? And this power, because you have to use different version of Young inequality, because here you have different homogeneities. And then for each, this term actually, this is quite easy, because all the W term have the same irregularity, which is minus kappa. So essentially, you need a bit of regularity of this term, and you need to separate the weight. But okay, I'm just telling you, if you care about this, this is, you see, these power are different, and if you try to do the computation, you don't pay attention to this. Maybe you end up with the L4 norm of Z without weight, so this you cannot control. Or you end up with the H1 norm of Z without a weight, again, you cannot control. Okay, so you have to be careful that you end up here. And let's assume that now I did this exercise and I obtained this estimate with a small delta. Okay, small delta is always possible because you do this Young inequality. So it's enough to have a small, a bit of space. If I had here 4 power, I would be dead. Okay, there is no way that I can control this because this has very large fluctuation, which I cannot control. So this term with a 4 power will never be controlled by a term like that. Okay, pathwise. Okay, this is, I'm doing computation for every omega. Okay, this could be 2 million. I still control with a small constant here. The price to pay this constant will become very large. Okay, so it's a balance. But you see that now the good guys won, but of course they have help of the ugly guy. Okay, now you see the pattern of, if you have seen the film, you know what I'm talking about. Okay, you need always the ugly guy to have the good guy win. Okay, the ugly guy is here because they are distribution. Okay? Okay, good. So the Italian Western tell you about analysis. Okay, let me write. I think this is the ugly guy. If you don't know what I'm talking about, I think you should watch the film because you missed very beautiful music, at least. Okay, so here we are. Okay, but you say, okay, this estimate is like for the variational problem, but I'm not looking at the variational problem now. I'm looking at an equation. So what does it buy me? So the equation was this. So let's see. I have good plus bad, so good. Good plus bad is 0. So good certainly is, okay, let me think what I want to say now. So what if I bound the good with the bad? Yeah, I think it's working. So let's buy, the good are positive, so certainly good is smaller than bad, okay? These are, because the sum is 0, okay? And now I'm done, okay? Because now this is less than ugly plus small good, delta good, okay? And then you have 1 minus delta good less than ugly. And now I'm done, okay? Now I'm very happy, okay? Because, you say, okay, they are ugly. Yes, they're ugly, but I know them. I know exactly what they are doing, okay? They have very predictable behavior. They don't surprise me very much, okay? So now you look what it means. It means essentially that rho 1/4 Z in L44 plus rho 1/2, this is Z1, because this is, let's say, what I'm interested in. But of course, you can control more than this, okay, with this argument. Yeah, actually, I could be more precise. I have this, and here I could replace this with it will work with the real object. So essentially tell me, I could always put the real object here. So the real object is something like this, H1 in the space, ds, okay? So this tell me something about the full trajectory, okay? Here I don't want to use this, okay? Just I didn't have space, I wrote that, but I could have wrote the other one. This is the good guy. And then this is smaller than Qt. Okay, this is what, up to a constant. Okay, I don't care about this cost. Okay, but you see, delta has to be small, otherwise I cannot do this argument. Okay, that's why I'm using that this is positive. Okay, now I have an estimate, which is beautiful, okay, because it tells me something about the solution only depending on the noise, which is very predictable, on the ugly guy, which is very predictable, because essentially some norm of my noise with a weight, okay? So you know that W belongs to weighted space, and actually it's integrable because of hypercontractivity. So the average of this thing, it's uniformly bounded, okay? So I have the average. Sorry, I wrote Qt, but who was complaining the last time and didn't complain again? Who was the one who, Carlo, you complained about the T last time? No. There is no T because I didn't have regularization. There is volume, possibly, but there is not even volume because I already removed. You see, in this estimate I did, in the estimate I told you, there is no volume anymore. The right-hand side is uniform in the volume. Okay, you have to trust that you can do it, but essentially, as soon as you have the weight, you can drop the characteristic function. Okay, so the volume disappeared, this estimate is uniform. So let's say Q lambda, this is finite, and therefore you get an estimate, you get the supremum over lambda. You have, yeah, technically, yeah, here I skipped a very unpleasant feature of this problem. This is, of course, not true. You should have, Carlo, you should have complained with me. I mean, this is what I would like to have, no? Then I wake up from my dreams and I look again at what I was doing, and this is not possible because, of course, here you have lambda, okay? So the good guy, you have the 4 power only inside lambda because in the potential, this coming lambda, and this is very unpleasant waking up, okay? Because then it means that this is not, okay, if you do this, you are still not working because in the good, let me write again the good guys who are, sorry. Let's write the good guys. The good guys are this, actually, okay? So essentially the good guys is this guy. And let me write it in this way, okay? I put the indicator function here. And then the other good guy is the other one I wrote, okay? Yeah, sorry if I make you rip your pages, but no, actually, you just have to. So this is in the full space, okay? This is L2 of the full space. That's fine because this is the entropy, and the entropy was the entropy of the Gaussian free field was in the full space. But unfortunately, the 4 power was coming from the interaction. Then I have only write it inside the volume because I didn't put it there outside the volume. I cannot put it there because think about how the problem. Okay, so. These estimates, you should be able, but the bad guys are in the volume lambda, so let's say bad lambda. Okay, so they are in the volume lambda, so I still have hope because they don't look outside. And actually, the only thing you have to change is that here you need the characteristic function. Okay, so the estimate you have like this is going to work, this is the exercise, but I think it's a reasonable exercise. These objects are only in lambda, so they should depend on lambda. I can make it this larger if I want. So the good guys are like that, and yeah, then the only thing I have to change is that I forgot, but this is, if I did from the beginning, you would have thought that this was very simple and you didn't notice, okay? But this is what happened in reality. You are very excited because it's going to work, then you say, no, it cannot work very easily, you have to deal, and it's a bit painful because this is, yeah, it's a function, yeah. Anyway, so the good guys are like that, and now the argument works, okay? Just you have to do this small change. The other one, it's fine. So it's not true that, yeah, now this object make you life a bit more miserable because it's moving when you take the infinite volume limit. So I ignore it for the moment, okay? I only look at the second one, which is very nice. So you have uniform, now what I have is that you have uniform estimates of these, yeah, let me write it in this way, okay? Okay. I have uniform estimates of this guy. So this depends on lambda, so I write it again, but just because I didn't want to write all the time. This is on L2 of the space. This is in the S, so this is finite, okay? Because this is bounded by Q. And Q does not depend on the volume anymore, okay? So this supremum is beaten, okay? We won, we won. Okay, we won. That's essentially give you tightness, okay? Give you tightness for Z, and then you get tightness for the sum of the two because one is not moving. W is always W. So from this you get tightness. Okay? Okay, so the volume, so you see you have a part of the good term only in the volume, so you use it to beat the bad guys. You have to do it here. So let's write it in this way so you recognize, so the ugly does not depend on the volume, but the good guys still depend on the volume, but that's fine, okay? This is the important point where what you pay here, you can repay, okay? You're not in debt with respect to the bank. And then where you are good, yeah, okay? You just made effort, okay? So you have good estimate. Okay, so this is the argument to take the infinite volume limit, okay? Yeah. In this model. So try to do it with the probability measure that we discussed. It's not. And this, so what we did, we obtained an equation which represents the trajectory of my field, and then using essentially PD argument, we obtain a priori estimate for the solution. This is true for any solution, okay? There could be many, possibly infinite volume, there is only one, but we don't care. Every solution, what you are saying is that every solution is a very mild information because essentially you have only a L2 control, but every solution is bounded by a constant of the noise. Of course, it's pathwise. Yeah, it's not really pathwise because I needed to, the first order condition is not pathwise, okay? So in this theory, it's not like SPD theory where you can do pathwise theory. Here, unfortunately, you always take the average. So this is a price to pay. Questions? Yeah? Essentially, I could have removed lambda also here, of course, because removing lambda, you pay more, so you can always allow to pay more. The point is that here, I'm not allowed to pay more, but with respect to the noise, I can pay more. That's because the noise, I know it, so I can estimate this object. I cannot estimate Z because Z I don't know, so the only thing I know about Z is this particular object, so I have to keep it like that. But the noise, if you want, you can put the indicator, but then you can remove it. It's not easy to remove because this is a distribution, but yeah, in the proof is a bit more, yeah, because this is not a smooth function, this is a distribution, so you have to understand if this is correct, but in the notes, everything is done correctly. I won't just avoid to talk. And you can remove it, getting a bigger contribution. Okay, so this is always possible. And why you didn't lose? Because it's true that I can remove it only because I have a weight. And as long as this power is positive, let's say this weight can be a polynomial weight, so this is a small power of a polynomial weight. I need it because, of course, if I want to remove the weight, this field grow logarithmically, so I need something to beat it. But as long as I can save, you see, I have to assign this row. I mean, it's another bank exercise. Okay, you have savings of 1 power of the weight, and you have to distribute to all your things in such a way that you save a little bit for W, you save 1/4 for Z if you want L4, and 1/2 in that. So in some sense, it's not obvious that it's going to work. So in the paper, we didn't do any abstract theory. We just computed for every time that it's working. Again, it's not very nice. One should have a general idea why this should work, okay? Why these two terms should control those, okay? But I don't have it. Yeah.
Are there any properties that we can impose on that way so we can take the first bound to be uniformly overall weight? So
well, this is uniform now overall weights. Yeah, but well, you say for every weight in a certain class, this implies.
If we make such a construction, it's not uniform. We chose some values of the weight.
Well, but I'm using, yeah, I mean, essentially you can replace, I think you can replace, yeah, I was revising the lecture. I think in the revised version I use a general class of weight because I don't like this, this very, so I think you can replace this weight with any other weight, which is nice. Like compactly supported weight should work, but I'm not sure. I need to do computation, but this should be my idea, that any weight you put, you should be able to. So for a large class of weight, the estimate does not depend exactly that this is the indicator function, really. Okay, I think we are using it maybe in one point. That's why I didn't change it right away, the notes. But in my mind, it should work for a large class of weights. I just didn't check it. Okay, like decaying, like yeah, like polynomially decaying weights should be fine. Because this Z, in the limit, what I expect from Z, it's really a decay polynomially, like the Gaussian field. Okay, so let's see how, I think, okay, so we end at half, 20 minutes. So I have 30 minutes, okay, for now. Yeah, maybe I wanted to make a choice. Okay, let's see if I make a choice or not. Right, this was an important point. I think we discussed it several. This clarified your question of before. I think we try to use them. You will see that maybe you grow familiar with them. So this is one way to use it, to do a priori estimate and get tightness. So we remove the dependence on the volume. Essentially, this is telling us that the size of Z in a weighted space is controlled by the size of the noise in the weighted space. Okay, so make your problem linear. What we can do, okay, let me cancel now. Go here. So we don't have a limit, we only have tightness. So with tightness, we can take converging subsequence. And essentially what you can prove, you have to pass to the limit, but essentially every limit point of, sorry, every accumulation point. So now I'm looking at the set of, so now I'm looking at the set of these minimizers, okay? So these are the minimizer, and again, this argument essentially give you tightness of this family of minimizer in some space of space-time functions. Okay, so as in, let's say you need of course you need to be, you cannot put one. So this object live in L2 H1. So you have an L2 bound of the H11 norm with a weight. So if you want to have compactness, you need to relax this constraint. So you need just a smaller space, like h1 minus epsilon in time and h1 minus epsilon in space, and maybe a slightly smaller weight. I don't know, I'll put 1/2 minus epsilon. So it will be tight in this space, okay? You will have limits, because you need a compact embedding to have that, right, proper. So essentially the elements are here, but the norm is always, okay, you have a limit here, but then the limit belongs to, so every accumulation point, so let's call it Z, some limit of, let's say, a sequence. You take a subsequence of volume, it belongs to H1T, actually belongs to L2 of H1T and H1X, and with the weight rho 1. Okay. So it has the same bound. It has the same bound, because the limit exists in a larger space, but by Fatou property, then you can pass to the limit in the inequality. Okay, so you mean you have this bound. Okay, you have a limit point and satisfy the Euler-Lagrange equation on R. Okay, so we obtain a field which lives on the full space and which satisfies the Euler-Lagrange equation in the full space. So it looks like this. I have to be precise now what is K, but essentially, so you have Euler-Lagrange equation for every K in, again, H1T, H1X, lock. H1X with compact support, let's say. Okay, so now the point, okay, so now the point is that you have the Euler-Lagrange equation, but you have to pay attention now, because the integrals are in the full space, essentially. So you risk that this object become infinity. So to be on the safe side, you assume that K is only compactly supported in space. Okay, so that the integral will be finite.
What did you write
as elements in this space? So the law converge in this space, in law. Okay, I should say the law of these processes, sorry. The law of these processes, but I'm meaning weak convergence of those processes. They converge in this space, and the limit is the law of a process which has this property. Okay, just for me it's easier to think at processes, but is the law. Okay, so you have just compactness of the laws, and then you extract a converging subsequence. You have weak convergence, but then the limit has also the regularity of all the sequence essentially. And also, it satisfies the equation, okay? And you have to pass to the limit in the equation, so this has to be proven, but this is true. So this represents, so every limit point is a solution of the equation in infinite volume. There could be more than one, I cannot ignore, but certainly this would, you don't have any other representation of the measure in the infinite volume, okay? So this is what is 542. So the point of view of the lecture notes is that 542 in infinite volume are solution of this equation, okay? Yeah, because the same argument will work here, okay? You can still write the forward-backward equation. Because these objects are actually local, so essentially you can still write that equation, okay? You can see from there, think about it. You see, maybe this is important. Maybe this is a good thing to observe. So the forward-backward equation, of course, exists in infinite volume. Okay, so it's something like this, and this is well defined in infinite volume. There is no infinite integral. It's just point-wise equation. Okay, for every x in R2, you should have this equation. And now the field is different from zero everywhere, because everywhere you have perturbation by the Gaussian field. Yeah?
Because the sequence of finite volume index is in H1 minus epsilon, 1 minus delta.
No, I'm just, sorry, I was rapid, okay? So the sequence by this property, so every law is almost surely in H1, but then since you have a bound here, to have compactness, you have to take a larger space, okay? And then you can use Prokhorov, because this function has compact level set, but in the larger space. But then the limit, yeah, because then you can use Φ2, so Φ2 always work, okay? So if you take the limit from inside to outside, you have to regularize and do, but if you take the limits from inside to outside, you just get a bigger thing. And the bigger thing is bounded, so also the prelimit is bounded. Okay, so this is standard functional analysis. You just need some slackness to take the limit. The limit exists as a distribution, but then you check that it's actually a function with regularity. And then, of course, you have to pass the limit in the Euler-Lagrange equation, but it's done in the notes, okay? You verify that the limit, the object also in the limit satisfies the equation, and from this to this is the same exercise we did last time. This is just the weak formulation of that equation, okay? You integrate with the test function, and in this context, the test function has also dependence in omega, so you have to integrate also with respect to omega. Okay. So, but you see now, so the forward-backward SD, let's say, is a description of phi for 2 in infinite volume, okay? On R2, you don't have a density anymore. That's the point, okay? So phi for 2 in infinite volume is singular with respect to the Gaussian free field in infinite volume, okay? So you don't have a description as a density. Well, I didn't prove it. Actually, I don't prove it even in the notes, but it should be singular. It's singular. Okay? Exercise prove it. Yeah, I don't. But this is even Ising model. It's not a strange property. Okay, Ising model on a finite box is absolutely continuous with respect to the Bernoulli measure, but in infinite volume is it not? Okay, and you just have to find a function which for the two does not behave correctly. But it's a smooth shift of the Gaussian free field, okay? So it's still true that X is W plus Z. Okay, so this is more robust than the description. Okay, but this is already known, okay? You take Brownian motion, you take twice Brownian motion. Twice Brownian motion is singular with respect to Brownian motion. It's very, okay? But this shift, so this shift is not in the Cameron-Martin space of the Gaussian free field in infinite volume, but is a good shift for us, okay? It's a smoother. Okay, so this is the main point of this lecture, is to advocate the point of view that stochastic analysis give you control which you lose otherwise, okay? So this is, okay, we did all this work because the limit cannot be expressed as a density, so the description with a density is not robust in this limit, but this description passed to the limit essentially relatively easy. Okay, let me see if I wanted to do large deviations. I have 15 minutes. Yeah, okay, maybe I don't have time to look at the exponential now. We will look at the exponential tomorrow. So I want to do it because I will do it rapidly, more or less it will work like this, but the exponential is convex. So I can prove that the limit, this equation has a unique solution in the limit. So this I want to do. So, so if you can prove that there is only one accumulation point, then you are done, okay? There is the limit. What we can do now, yeah, even large deviation. Okay, let's try to look a bit at large deviation. I will not be able to do all the argument. Just, I want to give you another use of this equation, okay? Now, we proved that every limit, so essentially I'm talking to you here about solution to the equation. Then I claim this is a description of phi for 2. I mean the following. Let's go back because, of course, I enlarged my problem. So let me maybe precise this point. So you see, you have your measures, phi lambda, and let's look, and somehow nu lambda is the law of the terminal point. It's the opposite, sorry. Okay, so it's the law of the terminal point of the finite volume measure. Any minimizer, let's assume there is only one. Any minimizer, okay? Then, so what will happen is that, there exists there exists a sequence of volume, so that this converge to some limit, let's call nu. Okay, this is essentially by tightness, and then this is also given by the law of Z1 plus W1, and this is any accumulation point, some accumulation point. Of the forward-backward SD, okay? I don't have control because I don't know if the FBSD has unique solution, but you see, essentially I took the limit of those sequences satisfy forward-backward, so I know that the law is the law of the terminal value of some solution of the FBSD. This is all I know, okay? If you give me if you produce in another way another solution of that equation, at this moment I don't know. You see, if you give me another solution and I don't know how you produced it, there is no reason that any solution, all the solution of this equation has this property that the marginal is exactly the same measure. So this is saying any solution, it's not even saying that because somehow you can have multiple limits, you can have multiple nu because I can choose different sequence of volume. In this problem, there is no uniqueness. I mean, we don't know how to prove it. Again, I told you that people expect that in high temperature, no, actually, because they prove it in other ways. In high temperature, this is unique. In low temperature, there are two. But in this approach, we don't see this property. It would be very interesting if you can find out a way to see this property, okay, to me, at least. Okay, yeah, I think. So what now I would like to do in 10 minutes, just give you an idea, because I want to do another application, is that even if we don't have a limit, so let's see, because it's starting to be, I think we still have some time, 10 minutes. So I want to mention large deviation. For phi for 2 infinite volume, okay? So this is a nice application because I know very little of this family of measures I constructed. I know that they have this property. They are the marginal of this process which satisfy Euler-Lagrange equation. But we still are able to prove large deviation, okay? So what is large deviation? I think not everybody is familiar, and you should not be. Just you now look at different measures. So to be fancy, I use H bar. So we're not only doing deep learning, we are also doing quantum computing. This object is just something. So is a small change. You just divide by H bar here. And then you have a partition sum which depend on H bar. And here you put the H bar. H bar is a constant, okay? It's a number, a positive number. And this is the GFF with covariance 1 minus Laplacian and H bar. Okay, so H bar is outside the 1 minus. Okay, so H bar, we will look at H bar very small, but positive. So we are looking at situation where the Gaussian free field is very small, and you perturb it with a very large fluctuation. Okay, if you say this is very strange, you should remember that this looks like that, This is just the potential plus the quadratic form. Essentially, this is phi. If you write the Gaussian measure in this way, then you see that this is coherent, okay? So you have 1 over h bar in front of the full action of the model. Okay, so this is a natural thing to do. It's a saddle point. It corresponds to a saddle point approximate computation, okay, saddle point, whatever. Okay, you are taking you're integrating the exponential of a very large function, and therefore you expect that this integral, this measure, concentrate in the minima of this function, okay? This is what you should expect. Okay, your function looks like, so nu lambda phi looks like exponential minus some action divided h bar d phi, okay? So you expect that you concentrate in the minima as h goes to 0. So these are large deviations. Now you want to prove this property, okay? You want to prove that you concentrate, and you want also to prove that you do it with a certain rate. So what you want to prove, so in this context, what is interesting to prove is you try to integrate some function like this, some function of phi divided h bar, and then you put the measure. Okay, and then you take the log. So what you expect, imagine if the measure does not change very much, when you take the log, you get f over h bar, okay? So to get some limit, you have to multiply by h bar, because this quantity is becoming very, very small. So you want to prove that this converge to a limit, and then we are going to prove that the limit of this, so this is going to converge as h goes to 0, to a limit which is the infimum, okay? Now you're looking, I need to perturb the measure to get something interesting. So I want to do something for every function f, but essentially you expect to take the infimum of the sum of the two, okay? So infimum over the functions phi, let's say, of the sum of f phi, plus what? Plus what was this action? The action was the integral of phi 4, and then there is the quadratic form for the Gaussian free field, so something like this, phi 1 minus Laplacian phi, and this is over the full space, maybe 1. Okay, so you expect something like this, and if we do it in infinite volume, so we expect here to have infinite volume too. Okay, so this is what you expect. This is what you want to prove. Okay, but I want to do it directly in infinite volume. So what we are doing is simply you construct again the measure. Okay, this is essentially the same computation, just you will have an h bar somewhere. So you construct the measure in infinite volume. And then for any limit measure, now you have a family which depends only on parameter h, but you could have, it's not specified. So what I'm saying is that any family nu h, which is obtained as accumulation point of the original family, will satisfy this property. Okay, I don't have uniqueness of the limit, but I have uniqueness of large deviation. And you can imagine why, because this potential is convex now. Okay, and again, okay, is this, okay, there is no weak products now. Weak product disappeared and seems magic, so it's not there anymore. So for any family, satisfy this. Satisfies this, okay, this limit with R. Okay, so this is the statement you can prove. Is in the proof is in the notes. I just want to give you the idea. I have 5 minutes, so I think it's enough. So this is a challenging problem because the family, you don't know, the only thing you know is what I've wrote so far, okay? And this is the natural way to look at this problem, and I want just to show you that the information we got are enough to solve this problem. It would be simpler if the potential was convex at the beginning, because then you have unique solution, then you take limits and you identify the limiting function. So how we do, how does it look like the Euler-Lagrange equation on R? Let's say for ZH. Okay, so ZH is now the minimizer of the energy, which has this law there. I took already the infinite volume, so lambda is pure. The Euler-Lagrange equation, now, of course, I transform, but exercise for you, you have to go back and you have to redo all the computation and see where the H come. And essentially, the Euler-Lagrange equation looks like this. So it's like before, so this is the infinite volume potential, but of course, when you take the functional derivative, it's local, so there is no problem. And the only thing that changes is that you get an H bar in front of the Gaussian free field. Actually, not an H bar. You see the covariance is proportional to H, so Gaussian free field is proportional to the usual Gaussian free field times square root of H. So you get something like this. Okay, this is the only change. This is the trial function, and then you have the quadratic form without any constant. Okay, this is important. So the only change is this one. Okay, this is a weak noise limit for this equation. Okay, so large deviation, this is weak noise. Okay, it could be, you could imagine that here you have the the covariance, so you could imagine why there is not H bar is because you have rescaled the thing so that this is the case. Okay, so this is exercise for you. So this is large deviation. So saddle point approximation for this functional integral correspond in the weak noise limit for this equation. And now you redo the a priori estimates we did, and the a priori estimate will work the same because you just put a constant here. You redo the a priori estimate. So by the same way, you get tightness of this family. So you get tightness for that. It's tight. It's exactly the same computation because the only things that happen is that you get H bar in front of your noise, so the Q will have an H bar in front. So you have some tightness there. And then it has a limit, so you compute the limit, and the limit is, I'm going very fast, just I want to give you a feeling. Okay, the limit, what is? Well, everything will be continuous in this limit, and you essentially you remove this term, okay, because this was going to 0. So this is really a weak noise limit. You say, you don't have uniqueness, so you cannot do very much with that, but you can prove that every sequence of Z will converge to a solution of the Euler-Lagrange equation. Sorry, this is an equation without this term. Okay, so the limit satisfy the equation with 0. Okay, Z0, Z0 just you put H bar equals 0. Okay, in the Euler-Lagrange equation. So don't let me write, just you remove this term. Now you have an equation where there is no noise. Okay, I remove the noise. Now you look at it very deeply, a few minutes, and then you realize there is a computation to be done, but you realize that the optimizer, first, it's a function, essentially, you realize that this object, is a given function, deterministic, time S. Okay, of course, depend on S. In time 0 has to be 0. But then if there is no noise, essentially there is no randomness. So you see here you have a H1 norm in time, and then the optimizer of the H1 norm, it's just a linear function. Okay, so this is a linear function. You're optimizing the H1 norm in time. And then you compute the right-hand side, and you verify that phi is a stationary point. So phi should satisfy this equation here, phi cube with any test function. You take Ks to be of the same form. You take test function in this way, and then you find that essentially the Euler-Lagrange equation give you that you have a relation like this, like phi 1 minus Laplacian psi. Okay, this is a computation this, you prove this, and then you prove that. You use this test function, and you get this for every phi. So for every psi. Yeah, I think there is a tree, is not important. So it means that phi solve an elliptic equation, okay? Sorry, I forgot that we had this. So actually, when you do this computation, you get an additional term. There is a term which is gradient f w plus z times h, okay? Because the potential is, you modified the potential a bit. So here, otherwise, this would be trivial because it would just go to 0. Essentially, you get an additional term, which is the integral of f phi psi, and then here you have a plus f phi 0. Okay, so some f prime phi, so the derivative of f. Sorry, I'm going a bit fast. Maybe I should not have done this. Somehow, this is kind of exercise. You take the limit and you verify that the limit, since it's deterministic, it has to be a deterministic equation, and this equation satisfies this problem. And now you realize that this problem is the first order condition of a convex optimization problem. Okay, so it's the minimum of some convex optimization problem. You take phi convex to do that. Okay, you have to take phi convex. And then this implies that phi is the minimizer of this problem, exactly. Okay? If phi is convex, you realize that this problem and that equation are the same thing because a priori, you see, this could be a critical point of a functional, but you don't guarantee it's a minimizer. But you look at this, you look at what is the condition for this, and it's the same equation, and you prove that this equation has a unique solution, okay, because of the potential is convex. Sorry? Here f prime, so gradient f. Yeah, sorry. Yeah, well, it's a one-dimensional function, so yeah, sorry. Oh, yeah. Well, it's a bit improper. I've been a bit fast, but let's say it's the derivative. Yeah, sure. Okay, so you see we have a problem which has no uniqueness, but in the limit, the noise disappears. The noise, the renormalization of the fourth order potential was creating the non-convexity. And then when this disappears, the only term, you see, inside here, the only term which does not depend on h is the fourth power. That's why you don't see the renormalization in the limit, okay? The renormalization is infinite, but it's proportional to h. So when you send h to 0, it disappears. The potential, only the convex part remain. And therefore, in the limit, you have uniqueness. Maybe tomorrow I will show you, I finished because we end at 20. So I have minus 3 minutes. So I will do next time because this is a good exercise. We will prove that this function has unique solution if f is convex. And this would be motivation also for exponential. Okay, so let me stop here. Thanks.